Okay, welcome back. Oops. Welcome back. We are.
Any questions? Yeah. When it has to Sonics, what was the last part of the question? Yes. Oh, okay, okay, yeah, good. So, so someone asked questions about immediates and the sign extension. So if you remember, I told you that we take the 32-bit instruction, and as I'm going to show you in this lecture, what is going to happen is that part of these 32-bit instruction going to be the immediate. So for example, let's say 12 bits. In many of the RISC-V instruction, this is a 12-bit. Okay, so we take this 12-bit, and then within the hardware, we have this unit called sign extension unit, okay? That basically takes a 12-bit data and then gives you a 32-bit data. And then you just physically hardwire this to the adder or whatever operation that you need to do. Actually, probably not going to have time today, but next lecture, we're going to talk about the macro architecture. You're going to see exactly like where each of these components are connected to each other. Yeah. Yeah, and then let me increase the, is it better now? Is it better now? No? How about now? Maybe I'll speak a little bit. Is it better? No? Okay. Do this way. Okay. So last time we were talking about different types of operands. I told you that there is registers, immediates, and memory. Registers is the one that we use the most because it's the faster to access. We then also talked about the immediates. And the immediates are the ones that allow you to kind of like just, work with constant values. And then the third one, which is also very common, is the memory. And we mainly were talking about the memory as the last thing. If you remember, I said the two main operations in the memory are stores and loads. Stores is when you provide the address and data to the memory and store the value into the memory. And load is when you provide the address and receive the data from the memory. And I told you that generally loads are a little bit more time consuming because you kind of need to wait for the data to come from the memory side. I also talked about different addressing modes and the notion of byte addressability. So important thing about memory is that things needs to be byte addressable, which means that individual lines in the memory will be byte by byte. So if I want to kind of interact with the memory in the 32-bit fashion, then essentially I need to create some form of a block. So I usually block them in 4 bytes together and kind of read and write in 4-byte fashion. And then we said the notion of like Indianness of whether you store the lower addresses in the lower bytes or higher addresses in lower bytes. So that's also something to think about. We also talked about the notion of alignment, and we said that essentially since we have this capability of byte addressability, we can actually use this capability when we are writing our programs as well, which means that, for example, if I just want to write to 1 byte, I can issue what we call a store B or a SB. If I want to write to 2 bytes, I issue a store half. And if I want to write to the entire 4 bytes, the entire 32-bit, then I use the command called SW or store word. Similar idea for the load. So I can do load bytes, I can do load half bytes, and I can do load word. And then the last thing was for the load specifically, since you are loading a smaller thing into a bigger thing. So if I if I want to load just 1 byte and write it into a 32-bit register, then there is the issue of sign extension that I need to also deal with. As I said, by default, we use sign extension. So load byte, it basically takes 1 byte, writes it into the register, and sign extend the rest. If you don't want to do the sign extension, then you use the word, you use the character U in addition to that. So load half word U or LHU means that I want 2 bytes, and I want these 2 bytes to be just written without sign extension. You have a question? So the question is, if we are loading, can we load, for example, read from one line of memory and write it directly to another line of memory? No, so you have to do 2 instructions. So you do a load and followed by a store. That's actually pretty common. Yeah. Mm-hmm. Mm-hmm. Yeah. Yeah, yeah. So the question is, if I'm, for example, loading 1 byte, which is only 8 bits, and I want to write it in a 4-byte register, then obviously I'm changing the first, the lower 1 byte. What happens to this rest, right? Like, what happens to these 3 bytes? It stays whatever it was. Yeah, yeah, yeah. So the question is, okay, then in that case, then this becomes kind of a random behavior. What should we do? So, I mean, this is the programmer's responsibility. Usually what we do is that we zero this out first. So I first make sure that, for example, I add register with number 0. Remember that x0 was always 0. So I first make sure that I push that into the register, so the register is all zeros. Then I put my bytes as I wish. X0, sorry. X0 is register 0 that is always equal to 0. So if I write X0 to another register, that register also becomes all zeros. Yeah, if you want to. But again, think about this as a variable, right? Like the way that we deal with variables and, shift left, shift right, masking, all those things technically happens in the register level as well. So you can zero them out, you can AND them with 0, you can, write ones on the top. These are all just capabilities that you can write. Once we actually write some programs, you will see that how this will play out. Okay. All right, so any other questions from operands? The number of operands that we have in RISC-V is at most 2. Remember, this is a RISC-based operation. So we have always like a fixed number of operands. For some instruction, this is 2. For some instruction, it's 1. In some cases, there's no operand. So there are some instructions that doesn't need any sort of operands. Okay. And again, why do we limit ourselves to the number of operands? Why don't we go with like 4 or 5 or 6? Because that kind of inherently gives us more parallelism. The reason is that, as I said, we want some predictive, deterministic behavior, right? So because these things needs to be actually implemented in hardware, so I don't want the variability. I want to be able to exactly know how much time, how much hardware I need, or how do I assign this, such that then I can basically make the hardware simpler as possible. So you will see this actually when we are designing the hardware. Okay, so I remember I told you that every instruction has 2 parts. There is a command part and there is an operand part. We talked about the operand part. Now let's talk about the command part. And again, I want to remind you that we are focusing on RISC-V, which is a RISC-based, which means all the instructions are the same size. And we are focusing particularly on 32-bit version of RISC-V, so all the instructions are 32-bit. Okay? So what are the instruction types? Similar to operands, there are 3 different types. We have the arithmetic operations. Later on, we're going to call this R-type instructions. These are basically ALU or arithmetic unit operations. Adding, subtracting, XORing, ORing, these type of operations that you do mathematical operations on the operands. Then we have memory operations, and this is just the load and store that I talked about. And remember, we have a bunch of different loads and a bunch of different stores, and now we need to understand how do we handle the data size and assign extension and all that. And then we have what we call the control flow operations. Control flow operations is basically telling us which instruction should we read next, okay? I'm going to actually talk about the control flow operations in details soon, okay? Let's talk about the simplest one, which is the arithmetic ALU operations. ALU operations are two kinds. One is either we take two registers and do some arithmetic operations on them, or we take one register and one immediate. So there are two possibilities. So either two registers or one immediate and one registers. And we usually save the results into another register. Since this is like a very common operations, we want to actually store the results directly into a register such that we can then quickly access it. If we want to write it into the memory, then we need to another instruction that is a memory instruction right after this, okay? So arithmetic operations takes a register or another register or a register and an immediate and write it to another register. Examples of this in RISC-V terminology looks something like this. So we usually in RISC-V, we write the command first. So for example, it's sub or addi or add or whatever. And then we put three operands that we have. As I said, some instructions may have less operands, some instructions might have more. So for ALU operations, we always have two operands, which we show it here. And then we have the destination of, register, the register that saves the data. So in RISC-V terminology and syntax, this is your destination register, this is source registers, and this is also source register, okay? So these are the rightmost ones are your operands, okay? The first one, basically what it does is saying that x3 is equal to x2 minus x1. And this one is saying that x5 is equal to x1 plus 10. And as you can see, the difference between the two instructions is that the first one is taking a register and another register as their operands. Second one takes an immediate and a register as an operand. And obviously, having two immediates is meaningless, right? So I don't want to do like x5, 10, and 10 because I can just change one of the 10s to 20s and get the same thing. So I mean, immediates comes as free, so I don't need to basically add immediates or subtract immediates, okay? Yeah, so that's kind of like, you know, the syntax. This is where we store things as well, okay? This is actually the full list of all the instruction, all the ALU operation instructions that we are using. As you can see, there are quite few of them. This table basically on the leftmost side, it shows you the label that we use. So when you're writing the assembly instruction, basically you use this label for that instruction. For example, addi, ori, andi, and so on and so forth. This is the full syntax. So it actually shows you what type of operands it takes. For example, addi, as you can see, it takes the RD, it takes a register RD, another register RS, and a constant number. So basically, this is, for example, in the example that I gave you, this is your X5, this is your X1, and this is your number 10, right? So immediate and constant, same thing. So we use this word interchangeably. You see constant and immediate, same thing. RS1 is register source 1. Since this is taking one register source and one immediate, you only have RS1. But if you, for example, look into the add instruction, you will see that it basically is similar syntax. It takes RD, RS1, and RS2. So the RS1 is still the same, register source 1. You take another register source as well, okay? And if you want the mathematical kind of equivalent, you will see that it's actually, we are showing it here to you as well. So you can actually, if you ever like wondering what these instructions do, you can always look into the kind of like some sort of a mathematical operation here as well. So this table is something that you can take a look at it and always kind of like reason about it. You don't need to memorize anything here. Just make sure that you understand these instructions. Let me actually break it down further for you. So as I said, I already spoke about add and add immediates. One thing to realize is that generally to make things simpler to track, RISC-V using this I terminology to differentiate between instruction that use an immediate as an operand versus instruction that use just two registers. So the difference between add and add-I is that they're same thing. Add-I just takes an immediate instead of RS2. As you can see, if you look further, you will see that we have things like OR and OR-I, which is also exactly the same. So OR-I and OR, both of them OR the two operands together, one of them two registers, the other one register and one immediate. Yes? Say the last part. So the question is, what is being given in your exam? You can bring cheat sheet, and we also might actually like print the table in the exam. But yeah. Okay, so add and add-I, we talked about. As I said, there is a whole bunch of others that are pretty similar, like XOR-I, OR-I, AND-I, XOR, OR, and AND. Another important thing is that we have a sub-instruction as well, which basically what it does is subbing RS1 minus RS2, so this minus this one, and write the results, sorry, this one minus this one, and write the results on this one, okay? One thing to pay attention to is that we don't use sub-I. The reason that we don't want to use sub-I is that essentially sub-I could be shown as an add-I. So if I do RD, RS1, and a negative constant, so like minus the constant, that becomes a sub-I, right? So add and sub is the same operation, just a negative sign. Yes? Yes, exactly. So every operation is signed. As I said, by default, everything is signed unless we specify this is not signed. In fact, there are some instructions, like for example, this instruction here, that this is an unsigned. So there is a U next to it that says that, okay, this is an unsigned operation. But everything else, integers generally signed, all the sign extensions are signed, all the data handling are signed. So as then naturally the constant is a signed value. So you can put a positive constant, which becomes an add operation. You can put a negative constant, and that becomes a subtract operation. Yeah. Yes. So the question is the sub instruction is RS1 minus RS2 right into RD. So RS1 and RS2, these are two registers already signed. So you don't need to do any 2's complement. They're both 32-bit. You can actually sign them, and then yeah, the results will be also signed. Yeah, everything's signed. Yeah. Good question. The question is, if I do immediate operation, is it faster than if I do two registers? The answer is no. So they are both the same size. We're actually going to design the processor such that it can read two registers at the same time. If it didn't read two registers at the same time, yes, that would be immediate would be faster. But we don't want that. Yeah. If you want to subtract from immediates, then again, so you can just do math operations. You do the negative of that, and that will be subtract from the immediates, right? So you want this, right? So so this is like x1 minus x2, or you want x2 minus x1, right? So you need to negate this, and then add them together. Yeah. You can negate the registers too. Basically, what you do is that you subtract it from 0 and it becomes negative, right? So if I write it this way, so if I do sub, let's say x2, x0, and x1, right? x0 is always 0. So this means that x2 is equal to minus x1. Does that make sense? So x2 now is a negative. Any other questions? Great. Okay, so these are all the other instructions. Then we have the other types of, so these are just regular, mathematical operations. In addition to that, we have other things such as shift operations. So we have shift right, and we have shift right arithmetic and shift right logical. So shift right generally means that takes the RS1, okay? Where is shift right? Yes. So we take shift right, take RS1, takes the value of RS1, shift it to the number that is shows in RS2. So for example, let's say RS1 is 10000110011 and some other numbers. And let's say RS2 is equal to 4. This means that shift this register 4 bits to the right. Okay? So basically becomes like, these two would be like, I add maybe 4 zeros here and then would be 1 0 0 and so on and so forth. Okay? I'll answer that question just in a second. Okay? So this is shift right. But as you can see, when I'm shifting things to the right, I need to decide what do I do with the sign operation. Okay? So do I sign extends? For example, in this case, do I put ones here or do I put zeros here? Because if I put zeros here, then basically I'm switching and flipping the sign. If I put 1, I'm basically sign extended. So this is the difference between logical and arithmetic. So that's why we have shift right L, which is a logical, and shift right, which is arithmetic. The logical one, it means that you just shift right. You don't care about the sign. That's why you see that basically here it shows you this word U. Means that just shift it to the right, don't care. This is basically this red one I'm showing you here. If you want to maintain the sign, then you do the arithmetic one. This is the sign version. Okay? So both of them is basically same format, RD, RS1, RS2. And as you see, you take RS1 and shift it that many bits that shows in RS2 there. But the difference between them is that this one is logical and this one is arithmetic. Okay? You had a question? Say louder. Oh yeah, good question. So the question is, are the destination and sources can be the same? Yes. But in fact, all three can be the same. So you can do x1, x1, x1 if you want to. Okay? So for example, think about like something that you want to increment, right? So you do, for example, you want to kind of like do 2 plus 2 plus 4 plus 4 and so on and so forth. So you can actually do add x1, x1, x1. There is no limitation. Yeah. Yes. Yeah. RD is equal to RS1 shifted to the right by the number that's shown in RS2. And it could be arithmetic or logical. Okay? We also have shift left, obviously. Shift left, which is the opposite. So you'll shift left RS1 to the number that's shown in RS2 to the left. But as you can see, shift left, there is no logical or arithmetic because on left side, you just put zeros. There is no sign extension when you're shifting left. So that's why you only have SLL or the logical because there is no difference between logical and arithmetic. Yeah. Yeah, you keep this first bit and repeat it. You get rid of them, yeah. So the question is, when you're shifting left or right, there are things that are going to be spilled over, and then yeah, you get rid of them. I mean, in fact, in Harvard, there's no where are they going? Like shifters. I don't know if you have like taken like logic courses, you will see how the shifter works. So basically just like a circular loop. Yeah. Any other questions? Yes. When you're shifting left, the question is, when you're shifting left, do you still maintain the sign? No, so you shift left, it's a dumb shift left, so it doesn't have no idea of what's going on. If you're shifting left, you might destroy the sign. Yes. Shifting left technically should, yeah. If it's a positive number, yeah, shifting left makes the number bigger. Yeah. Again, it's like very similar to the way that you write it in a C, C++. Same idea, right? You would shift left, right. You do this bit-based operations. If you specifically take like low-level operations, you would need that. Okay. So this is another thing. The last thing that we haven't spoke about is this SLT and SLTU. Uh, uh, SLT is set less than. Okay, so it sets the register if it's less than. So the mathematical operation is shown like this. Okay, so basically what it does is that it's compare RS1 with RS2. Okay, if RS1 is less than RS2, then it sets the register. It writes 1 to RD. Okay, so this is kind of a binary operation. So it's either RD after this operation is equal to 0 or it's equal to 1. Okay, if RS1 is less than RS2, RD will be equal to 1. If not, RD will be equal to 0. Okay, and then since this is a comparison, the comparison can be signed or unsigned. So that's the difference between SLT and SLTU. SLT compared this sign-wise. SLTU just compares the absolute values. Okay, that's the difference. All right. And then we can have an immediate version of that as well. So instead of comparing RS1 with another register, you can also compare it with an immediate. Okay, so I have SLTI and SLTIU. So I can compare it with an immediate sign-wise. I can compare it with immediate unsign-wise. And you can see this would be very helpful, for example, for your for loop and while loops. You want to see whether your loop has reached to the end or not. Okay. All right, I think I looked at I gave you an explanation of all of these instructions. Is there any questions here? And again, you don't need to memorize any of these. You can just need to understand, and it's fairly simple. You just look at the table and you kind of can follow what's going on. It's just to give you some understanding of how these instructions are working. Good. Perfect. Here's an exercise for you. See if you can find the final value of x3. This is also opportunity for you to post it on CampusWire if you want. Write your answers. Yeah. You can bring a few pages. I'll explain how the process will work. Yeah. The question was about the exam and how many pages of cheat sheet you can bring. Okay. Any questions here? All right. So yeah, if I want to give you this one basically says x0 plus 3 and write it to x1. Remember, x0 is always 0. So basically this means that x1 will be equal to 3. Same idea here, x2 will be equal to 5. Then we're going to add x2 and x1 together and write it to x3. So this would mean that x3 would be 8. And this one says shift right arithmetic, x3 with x1. x1 is 3. So x3, if I want to write it down, would look like something like this, right? Another 0, right? And if I shift this by 3 bits, it's going to become like 0, 0, 0, 1. And the rest of this is 0, so it stays 0. So the final value would be 1, right? Any question here? Yeah. So the rest of this, so this is 8, right? So the rest of this is all zeros. Because this is a positive number, right? So if I want to write this in the binary format, I just put 8 and then the rest will be 0. Okay? So this is 32 bits. These are the 4s. This is the remaining 28, right? So, and then I shifted right. It's just zeros coming. Yeah. If you logically shift right, this same results. Good? Yeah. X0 is always 0, yes. Even if you write it to it, it stays 0. So if I have something like X0, I don't know, like here, if I would have like X0, X0, and 5, X0 stays 0. Doesn't become 5. All right. So we're going to have a bunch of these examples, further examples in the homework. And if you go to the discussion sections, there will be some examples there as well. So if you want to practice more, you can do it. Here's another kind of like a example for you if you want to do this further. So if I want to do something like, if I want the sum of these 4 values, and then I want to shift left y and shift right y and then subtract them from each other and write it to z, write the assembly sequence of assembly instructions that does this operation for me. You can write it down and post it on CampusWire and people can comment on it. Yes? Yeah, y is a variable here. You can choose any registers, exactly. So in the compiler, I'm going to later show you how the compiler chooses these registers. Typically, there's like a few of them that are usually used for temporary variables, and there are a few of them used for other stuff. But yeah, technically, you can just start from X0 and then move forward. Yeah. Perfect. So that's it with the arithmetic operations. As I said, you're going to see a few examples in the discussion sessions and the homeworks. So hopefully that will help you to understand this further. Let's move on. Let's talk about memory instructions, okay? Remember I told you that we have load and store. These are the only 2 that we care about. The way that we actually kind of do the addressing mode in RISC-V is we use a base plus an offset, okay? The base is a register. The offset is an immediate, okay? So the way that we address memory, either store or load, is that we provide a base, which is a register, and then an immediate, which is the offset to that. And as I said, the way that we read it, we can read it through word or half word or bytes. We also need to take care of sign and unsigned, okay? So here's the list of instructions. Here's the syntax that we use. So we do LB, for example. RD, this is the destination register. For load, we need to read something and write it to a register. RD would be that. Then the way that we show the offset and the base is we put the base into the parentheses. So for example, this could be x1, and we put the number outside. So for example, let's say 20. So this means that whatever value x1 has, add 20 to it, and that would be your address, okay? So basically, this is the kind of the mathematical equivalent of that, okay? So we take the address, and address is basically, address is RS1 plus offset, okay? So we show it this way. If you don't like, sometimes we also show it this way, okay? So if you see this, this is the same thing. RD, offset, comma, RS1. So this is also possible syntax. This is also a correct syntax, okay? We typically show it this way. So we put a parenthesis to kind of show that this is the base, this is the offset. Yes? There is no shifting. So this is just an immediate value that you add. There is no shifting. Yeah, the value. Think about this as a decimal value. You take that value, you add it to whatever number that is stores there, and then that would be your final value. So for example, let's say I store like 300 in my X tree, and the offset is, for example, I want to address 50, like 350, address 50. So I put the offset equal to 50. So this is the way I'm going to write this. So let's say, and then I want to store this value to X4. So I do LB X4, this is my destination register, 50 X3, okay? So this is the syntax I'm going to use. What this says is that whatever value is stored in X3, which is in this case 300, plus 50, which means that the address now is 350, go grab 1 byte in the address of 350 and write it to X4, okay? And then same story with LH and LW. The addressing does not change. I think someone asked last time that if I want to read 4 bytes, do I provide 4 addresses or just 1 addresses? The answer is only you provide the first address, the beginning of that 4 bytes. That's the address that you provide. The memory understands that it needs to just forward 1 byte, 2 bytes, or 4 bytes. You just provide the first address, okay? You had a question there? The address is a number. It's a signed decimal number. It's not bits or bytes. Just a number. Yeah, yeah. Load byte sign extend, yes. As you can see, load byte sign extend. If it's LBU, which we have it here, it doesn't sign extend, okay? So it basically 0 extend and then put it there. So this is a good question. So if I want to write just 1 byte, again, this question came out earlier as well. What happens to this? One option is that if I just if I just put zeros and then write it there, that's one way. And in majority of cases, especially when we design this, we're going to later come back to this. You can, for now, assume that we don't write anything to the rest of the memory. So you just replace that 1 byte and not the rest. Okay? The sign extension, I'll show you when the sign extension happens as well. For now, just think about it mathematically. Well, I'm going to show you the entire hardware, and you're going to see exactly the hardware parts. Yeah? Is the base that support, say the last word, Lalo? Paging. Yes, paging, we're going to get to the paging later in the course. For now, every address is physical. So the question was, does RISC-V base support paging? Paging is a concept for addressing when we have what we call a virtual address versus physical address. We're going to have just one full lecture on virtual addresses and how we translate on that. For now, all the addresses are physical. So when I say 350, I literally go to the address 350. Good. As I said, so here, if it says 0 extend, here means that I just basically put all zeros and write it. But as I said, this could varies depending on the implementation. This table is just an example. Okay? So we have LH, LW, LBU, LHU. So the only difference between them is how much do we read? As you can see, this one basically says that I'm reading address plus 1 and address colon. When you see colon like this, so when it says, for example, memory 2 colon 1, this means that address 2 and address 1 concatenated together, okay? So for example, this is the terminology that we typically use in Verilog as well. So if you see something like 3 colon 0, means that address 0, address 1, address 2, address 3 concatenated together, that's one value, okay? So for example, in this case, since this is only 1 byte, I just put one number. This one, since this is 2 bytes, I do address and address plus 1. This one, since it's 4 bytes, this third one, since this is 4 bytes, you can see that it's address plus 3 colon address. It means that address and address plus 1 and address plus 2 and address plus 3, 4 of these concatenated together, that would be the final value. Make sense? Yes. Could I repeat what zero extend is? So zero extend means that I basically just add zeros to the rest of my data. So as I said, in this case, basically when we are loading 1 byte, since it's only 8-bit, I need to decide what I want to do with the rest. I can either zero extend it or don't do anything with it. All right, and then same story with store. There is one catch with store that people usually confuse. Store does not have any destination register, right? Because you're not writing anything to the registers. You're writing from the CPU to the memory. So there is no RD in store instructions, okay? So basically what you have is only RS1 and RS2, okay? We keep RS1 as the base. RS2 is the value that you want to write to the memory, okay? And be very careful because basically when I show you this instruction like SB, so let me actually give you an example like this. Let's say I have load B x3, 5, like 8 x1 for example, and then I have SB x3 8 x1. So looks exactly the same. The difference though is that in the spot in the top one, this is your RD, this is your RS1. Here though, this is your RS2 and this is your RS1. So this is a source register in the store instruction. For the load instruction, that's the destination register. You actually write to it. In the source, you write from it. Okay? So that's, just keep that in mind. They look similar, and they're different. Okay? The rest is the same. So again, you provide just one address. As you can see, again, when I use this terminology here, it means that I write only from bit 0 to bit 7, since I want to just write 1 byte. I don't want to write the rest of it. If I want to write 16 bits or 2 bytes, I do 15 colon 0. Means that bit 0, bit 1, bit 2, bit 3, all the way to bit 15. And if I don't provide anything, means that write the entire thing, which is the entire 32-bit. Okay? Yeah. No, so in the store, you are writing from the register to the memory, right? So whatever value that is stored in RS2 will be written in these addresses, okay? In these 4 addresses. It's address 1 and +1 and +2, +3, and +4. So 4 operates. So 4 bytes, 1 by 1 is written into these 4 addresses. Yeah, offset is an immediate. And it could be a negative number as well. So you can actually go up. So your base could be negative number. So for example, you say that, okay, address 300 minus 50. So you write it in 250. Each memory address is a byte. Yeah. Yes, exactly. So 15 to 0 means that we are writing lower addresses too. But if it was different, then it would have been address colon address plus 1, something like that. So that would be the opposite. But I mean, RISC-V is going to use Little Endian, so you don't need to worry about how we would do it in Big Endian. Yes. The colon syntax? Store half word, sure. So store half word, what's going on? So store half word, you want to first compute the address, right? You compute the address by taking RS1. You're taking RS1, sorry. You're taking RS1, you add it with offsets, that would be your address, okay? And then you take whatever value that is stored in RS2 and write it to that address, okay? But since this is a store half word, RS2 itself is a 32-bit value. You just take the bit from 0 to 15 and write that to the address and address plus 1. Because address is an 8-bit, address is only pointing to an 1 byte memory. So you write it the first 1 byte to address, the second 1 byte to address plus 1. Okay, so this is basically what the syntax is saying. It's saying that take memory, look at address and address plus 1. I told you this is a concatenation. Take register RS2 and look at the bit 0 all the way to bit 15 and write it into these two addresses. Yeah. You always provide the offset. So if it's 0, you provide 0. The base can also be 0. For example, many times you will see an instruction like this, like store word x3 8 x0. So if you see something like this, means that literally the address 8, like the base is 0. Okay. Let's talk about the third one, which is the control flow. We can have like a quick, maybe 5-minute break, and then come back to this. Okay. Okay, let's talk about control flow. Quick announcement is those of you who wants to come to the honor section, it's right after this class. Just come to the class. We will talk about that. Other than that, yeah, that's there is also the TA lecture session today at 4 to 6. If you wanted to go to there, go. All right. So let's talk about the last part, which is the control flow. Remember I told you that we are following this system or format called store program computers, or one Neumann machine. In one Neumann machine, we are considering a program as a sequence of instructions that their order matters. And we have this specific register called program counter, or PC, that keeps track of the current instruction that we are executing, okay? So if you want to run any instruction, all I need to do is changing the PC to point to the address of that program. And remember I told you that instructions are also stored in the memory. So essentially what I need to do is basically changing the address, or the value that this PC is storing, that is pointing to the address of that system, okay? So that's kind of like the idea of the PC. PC itself, you can consider it as a register. So it's similar to your general purpose X1, X2, X3 registers. But PC, you can now like add two numbers and write it directly to PC. It's not directly accessible by software to traditional way that we are doing, like X02 all the way to X31. So we have this thing called general purpose registers, which are X0 all the way to X31, and they're stored in the register file. We store PC somewhere else, so we will actually show you later. But PC is still a register, operates as a register, but technically is different, okay? All right, so when we are not changing the PC itself just increments so that we write the continue executing the program. In a store program order, we basically consider a program to be linear, which means that if the first instruction is here, we consider that the next instruction is right after it, and the next instruction is right after it. So everything is linear, okay? So essentially what we do is that the PC initially starts to the beginning of the program. And for example, if I want to run this, basically, excuse me, what the operating system does for us is assigning the right starting point value for the PC, and the rest of it will be taken care of by the hardware. And then afterwards, I don't need to do anything. I can just increment PC by one value, go to the next instruction, and execute it. So essentially, the program will be a continuous parts of the memory, okay? But there is a catch here, and the catch is that, remember I told you that instructions needs to be, the memory needs to be byte addressable. So each line is just 1 byte. But I also told you that RISC-V instructions are 32-bit, okay? So when we are reading an instruction, I basically needs to read 4 of them together to create a 32-bit value, okay? So as a result, when I'm doing PC, I don't do PC plus 1 for the next instruction. I need to do PC plus 4 for the next instruction, because the PC and PC plus 1 and PC plus 2 all belong to the same instruction, because PC is basically pointing to the beginning of the instruction. PC plus 1 is the second byte of that instruction. PC plus 2 is the third byte. And PC plus 3 is the fourth byte. So if I want to go to the next one, I do PC plus 4. Okay? So just know that our next, quote unquote, next PC, which is pointing to the next instruction, is always PC plus 4 away from the current instruction. Okay? So when we are talking about the microarchitecture later, you're going to see that the adder that we're going to use is plus 4, plus 4, plus 4. We're not going to do plus 1, plus 1, plus 1. In fact, if you do plus 1, there's going to be an error in hardware, because remember I told you that we don't allow misalignment. So we don't let the instructions to read from half of the instruction. Okay? And this is actually in CISC-based architecture, this is allowed, but in RISC-based architecture, this is not allowed. Okay? But then there's also another problem, and that problem is branches, okay? So think about an example like this, that you have an if then else code in your program. This is very common. You have loops, you have if then else's and things like that. So let's say, for example, I write this if then else's like this. So I have a sequence of instruction here. I call that block A. So these are just sequence of consecutive instruction. We usually call this a basic block. A basic block is a sequence of instructions that are continuous in the memory, okay? So I put basic block 1A here. Then I have an if condition. And depending on the value of x and y, I might run B block or C block, okay? So how do I choose which one to execute? Basically, what happens is that I need some mechanism that makes this check, and based on that makes the PC equal to the beginning of here or beginning of here. So I need some form of a PC manipulation functionality that, based on the value of x and y, change the PC to either beginning of code block B or code block C. Another challenge that you will see is that, remember I told you that memory is linear. This means that if I just put block A and just run it PC plus 4, PC plus 4, there is that at some place I need to jump over things. Either if I put, for example, C first and B next, if the branch is taken, I need to basically jump over this C block and go to the B block. If the branch is not taken, I just continue normally, but when I reach to this point, I need to jump over B and go to D, right? So it's kind of like a basics of the if then else operation, right? So for this, I need a mechanism to be able to change the PC and change this PC based on some conditions, okay? So this is where we actually gonna use these two important operations that commonly used in RISC-V and any other ISA, which is the jump instructions and branch instructions, or conditional jump instruction and unconditional jump instruction. This is the terminology that we use, okay? So when do we need these type of operations? These are, as I said, very common. Typically, we use them when we want to check a condition. Examples are if then else's, switch cases, and so on. Loops is also the same, right? So in loops, you run a few instructions, you check a condition, you either jump back and continue, repeat doing this, or you just end the loop and then move forward. Same for while loops and so on. Another scenario that you definitely need to kind of jump over things is when you have function calls and function returns, right? Your function might be stored somewhere very, very different in memory than where your, for example, the current routine is. So for example, let's say you start from the main function, at some point you need to call a function. That function might be stored in a different place in your memory. So you need to basically change the PC to point to the beginning of that function, okay? And the same story for return. When you're done with that function, you need to go back to where you were before. So again, you need to manipulate your PC to go back to where you were. And then there is also things like exceptions and interrupt. When the operating system wants to intervene, the way that operating system intervenes is that it basically takes control of the PC and point to PC to the function that is controlled by the operating system. This is how the operating system and the regular program interacts. Basically, they just manipulate the PC in order to achieve what they want to achieve. Okay? So let's see how we actually implement this in RISC-V. We start with jump instruction. Jump instructions are just changing the PC without checking any conditions. So this is what we call unconditional jumps, or generally just jumps. Okay? So jumps basically needs an important thing, which is where to jump, right? So the important thing is I need to know what is the target address that I'm jumping. In RISC-V, we typically do this by what we call a PC relative addressing. That is, I don't care about the absolute address. I just basically just need to know the target address. Where is it in comparison with my current PC? For example, saying if you want to jump to another address, you do PC plus some offset. Okay, so this offset, for example, could be, for example, if I go back here, let's say each one of these instructions are 4 instructions. I need to jump over 4 instructions to go to the next one. And remember, each instruction was 4 bytes. So I need to jump over 16 bytes to jump over this part of the block. This block, if I want to basically jump over it, I do PC plus 16, and then I'll go to the next block. Okay? This value depends on how many instructions I have. If it's more instructions, then I need to jump higher and so on. Okay? I can also jump back. How do I jump back? I do PC plus a negative number. So if I want to, for example, jump back 4 instruction back, I do PC basically minus 16, right? And so on and so forth. So depending on the size of instructions, the number of instructions, I can jump forward or backward by manipulating the offset. Okay? This is called PC relative addressing. Okay? And then important things about jumping and branching is that jump always changes the PC. This is what we call unconditional. And branch is an equivalent of jump. It changes the PC, but only if the condition that it's checking is true. So for example, we have an instruction called branch equal, which what it does is check the value of RS1 and check the value of RS2. If they are equal, then it changes the value of PC. If it's not, then it doesn't do anything. Doesn't do anything means that we just continue normally. PC plus 4, PC plus 4, PC plus 4. Yeah. So the question is jump is only used for function calls? No, there actually would be like things like switch cases as well, right? So for switch cases, you want to also jump. Yes. There is no call instructions. There is only jump instruction. We're actually going to give you the list. But there is, in RISC-V, there is this notion of pseudo instructions, which call is one of those that I'm going to talk about it. So you will see it. Yeah. Yeah, so the question is how, like, when the jump is changing the PC, does when you actually write the jump instruction, that's actually literally change the PC. Yeah, I'm going to show you the exact syntax in just a few slides. All right, so there's another thing that is specific to RISC-V, and that's the linking operation, okay? So RISC-V is using this thing called jump and link, okay? The jump part is regular as what you have learned before. This is basically changing the PC. The link part is remembering the current PC and storing it into the destination register. Okay? Why do I want the linking part? The linking part is useful when I want to return. Okay? Because when I want to return, I need to always go back to where I came from, right? So the link is basically used to store things in to remember the current PC. Okay. Uh, Many of the jump instruction or branch instructions does not need the linking part. So you can always link it to x0. If you link it to x0, you basically just don't link it, right? So the jump and link instruction is always there. You can link it to a proper register, and that way you can actually remember that address. Or you can link it to 0, and that means that you don't store it. Okay? So let me actually show you the syntax, and you will understand the differences. So RISC-V has these two unconditional branches, JAL and JAL-R. JAL stands for jump and link, and JAL-R stands for jump and link registers. We don't have just a regular jump like J. That's a pseudo instructions that you're going to see later, but these are the two instructions that you use. So jump and link, basically, what it does is that it takes the label, and I'm going to show you how we actually compute the label, and change the PC with that value. So basically what happens is that label is equal to PC. So you provide a number, that number will be stored in the PC. Okay? And since this is a linking operation as well, it also saves PC plus 4, which is the next instruction, into the destination register, which is RD. Okay? So if this was just a jump instructions, it would have been like this, jump label. That is, take the label, write it to the PC. RISC-V guys, for some reason, decided that, oh, I need to make this slightly more complicated and add this and link, which is basically the second part. That is, I take the PC plus 4. The reason PC plus 4 is that I want to remember the next instruction. I don't want to remember the current instruction, because if I jump back to the current instruction, that will create an infinite loop. I go to the next instruction, right? So I remember what is the next instruction and store that into the destination register, which is RD, okay? So that would be basically the instruction that we create, okay? And another important thing, which is kind of I'm showing you here, there are two ways that you can generate label, and this is compiler support in RISC-V, okay? You can write this way when you're writing an assembly code. For example, you say jump and link x1 and label x. Let me actually call it something. Let's say call it taken. Okay? So this is called label. This is actually written in English. Okay? So it's a word that you can use. Okay? And if you write program in assembly, you will see that there is like a flag like this. So it's taken and then an instruction here. Let's say, for example, add x3, x2, x1, x2. Okay? So what does this say? Is that, and then in between there might be many instructions. It doesn't matter. So what does this say is that when you write it this way in assembly language, the compiler will understand that what you mean there in your JAL x1 taken is go to the beginning, go to this instruction basically. So it finds that label taken and go to that instruction. Okay? So compiler gives you this capability. This makes your code very readable, because basically you can just follow along where your labels are, and you can have many different labels. Of course, you cannot use the same word or same label multiple times, because then that will create a problem. But you can do it this way. Okay? Hardware, although, does not understand labels and English. When you're actually writing this in real hardware, what you would do is that your label, the address that label pointing to, the address taken is basically equivalent to PC plus offset. Okay? Or let me actually write this as immediate, because it's easier for people to understand. So when I'm writing it as an actual instruction, a 32-bit instruction, I provide the immediate value. Okay? For example, I provide 16. What this means is that whatever the current PC is, so at this point, let's say the current PC is 8, this instruction will be translated into whatever value is stored here, which is in this case 16, add 8 plus 16 and go there. And then if this instruction is 16 instruction away, then, sorry, 4 instruction away, then you go there. Okay? So what I'm trying to say here is that there is a difference the way that you write it in assembly language versus the way that it's actually, in fact, implemented in hardware. In hardware, we map this as an immediate value, which is we need to basically compute the distance between this instruction and this instruction. And that would be the immediate value that you put there. In assembly language, you can just make your life easier. Don't compute that number. Just use the same label here and here. The compiler automatically calculates that immediate value for you. Okay? So you don't need to, as a programmer, you need to like have a calculator and count the number of instructions and like divide it by 4 and do all those things. You just use a label, and the label, the compiler will automatically compute the immediate value for you and put it into the right instructions. Okay? Yeah. The label does not contain, the label that you use in the assembly language is just an English word. It's not a number. The compiler basically counts the number of instructions and will find it. So I mean, there are a whole bunch of like how the compiler actually understands things is that it's a very, very complex process. But yeah, it's basically counts the number of instructions, compute the distance of these two instructions, and then figure that out. So it's like they call it compiler passes. So it actually goes through multiple paths. Unfortunately, we don't have time to go through how the compiler generates these things, but compiler does actually lots of complicated stuff. For example, how do I even know what to generate, like what registers to use, what labels to use, how to even like translate function calls to this. All of those things are done by the compiler. Any other question? Okay, so don't be confused by these two terminologies, okay? So the label is basically equivalent of PC plus the immediate. As I said, the addresses are always PC relative, okay? Then we have, the second thing that we have is JAL-R. The difference between JAL and JAL-R is using not PC, but RS1 as the base, okay? So the difference between JAL and JAL-R is JAL is writing label to the PC, which is immediate plus PC. But here, if I want to jump to a very different address, very large address, then I basically say that whatever value that is stored in RS1, add that to the immediate, to the offset, and write that to the PC. Okay? That's how we actually, use JAL-R. So our base is no longer PC, but the value of RS1. And this is useful for function calls, for example, because function calls are typically very, very far away. They're not within like 4 or 8 or 16 distance of the current PC. There might be 1,000 and 1,000 lines away. So that way, I basically write the base, the location of the beginning of that function in RS1 and jump it to there. Okay? The linking part, though, is the same. So as you can see, this top part, the linking part is exactly the same. The difference is this PC part. So this one takes RS1 and offset and write it to the PC. The other one is just taking the label and write it to the PC. Okay? There is also this one bit here. So this is a little bit weird, and people always confuse of why we are doing it this way. So what this one says is that we don't just take RS1 plus offset and directly write it to PC. We always make sure that the least significant bit is 0. So we basically force 0 to be the first bit. We don't shift it though, right? So as you can see, we take 31 to 1 and then add a 0 here. So basically, we force the first bit to be 0. Why? Because RISC-V does not like misalignment. So it does not like the addresses to start from odd numbers. It always wants the addresses to start from even numbers. Okay? So that's why in hardware, we actually force this, that even if you add the numbers, that it becomes an odd number, it forces it to become 0. And then another question that you might ask is that I told you that addresses should be multiple of 4, but here is basically making sure that these are multiple of 2. Why not we are adding 2 zeros here, right? So that's also a valid comment. The reason that we are not doing 2 bits is there are some instructions called compressed instructions that are only 16 bits. I told you that everything is 32 bits, and we're going to just consider those instructions. But RISC-V also supports 16-bit instructions. So there are instructions that can be multiple of 2 and not multiple of 4. Just keep that in mind. But we're going to just maintain this compatibility. But in our case, we're not going to see any instructions that are 16. So even if I do 2 bits, the result would be same for us. Okay, just keep that in mind. Good? Questions? Yes. Mm-hmm. Yes. Yes. It does, that does not. So the difference between the two is that the first one computes takes it, find the label, computes the distance between them, put that number as an immediate. In hardware, you take the immediate, add it to the PC, and that's your destination address. In JAL-R, we don't care about PC anymore. We take whatever value is stored in RS1, add that to the offset that we also provide. So we also provide the offset. So we provide RS1 and offset. We add these two numbers together, and this is your new PC. So the new PC could be millions and lines away from the current PC. That's okay. Yeah, so you can see like the reason for this is that you're basically limited by the size of immediate. You cannot jump far away because you can only jump PC plus immediate or PC minus immediate, right? And your immediates, as I'm going to show you later, at most can be like 20 bits or whatever, okay? So you can only jump to 2 to the power of 20 or 2 to the minus 20 in the memory, but memory is usually much, much larger. So if I want to jump really, really far, I jump using the registers. Yeah. What is the exact flow? That's also a great question. And again, that will be the microarchitecture question that I'm going to show you next. The next lecture. Yes. But I mean, just very short answer is that everything happens in parallel. So you add things, you change everything happens in parallel. Yeah. Label is literally a word that you use when you're writing the assembly instruction, like taken. So you're going to see some examples of instructions. You can use whatever label that you want. So name of the functions, for example, foo, bar, these are labels. Yeah. So if your label is very, very far, that the compiler cannot translate it to immediate, either you're going to have some compilation error, or most of the compilers are smart enough that translate this into multiple calls. So it actually translates it into RS1. So compilers are really good. So they can actually understand these things. And so again, you can just set and forget kind of thing. But the link one is a separate story. The link one is just for remembering your PC plus 4 for cases that you want to return. In majority of cases, you don't want to return. So the linking part is basically useless. Yeah. It could be a function name as well. Yes, yeah. But then when you're writing the program, you have to basically use it this way and colon, and then the first instruction starts right after. That means that go jump to that location. Yes. No, you can never actually use PC directly in your instructions. So there is no instruction in RISC-V that you have PC as an operand. So you cannot directly manipulate PC as another other registers. The only way that you can manipulate PC is with JAL and JALR. That's all. And branch, basically. Okay. So then in addition to the jumps instruction, which are unconditional jumps, you also have conditional jumps. RISC-V has this 6 different type of branches. Branch equal, not equal, less than, greater than, less than equal, unsigned, and greater equal, unsigned. The syntax of them are all the same. So basically, you have your instruction, you have RS1, RS2, and label. Okay? So what does this say is that in this case, if RS1 and RS2 are equal, jump to the label. Okay? If not, your next PC is PC plus 4. Okay? So this is basically kind of like this logical syntax for it. It basically says if RS1 and RS2 are equal to each other, write label to PC. This is else. Else PC plus 4. Okay? Same story with not equal and less than. The only difference between them is the mathematical operation. So not equal means RS1 and RS2 are not equal, obviously. Less than means that if RS1 is less than RS2 and it is signed. If you don't like the signed version, you can also have the unsigned version. So RS1 unsigned less than RS2. Then you have greater and equal sign, and greater and equal unsigned. Yeah. Yeah. So the question is it required that your next, your taken parts, the taken path be relatively close? Yes. Then it should be like within the size of the label, which is not that bad. It's like 2 to the power of 20 bits. So it's not that close. Yeah. But again, compilers can fix those issues for you. Yeah. So question is, are there, for example, less than equal? So I'm going to show you pseudo instructions that basically extend this. But technically, logically, you are good with all of these. You don't need less than equal. You can basically have 2 different branches or change the sequence, and that becomes less than equal. Okay. So this is just reminds you that these are PC relative instructions. And then also all the branch instructions are based on the label. Okay? And then as I said, just emphasizing why are we using that 0 bit is to make sure that the beginning of the address is always an even address, because we want to go by multiple of 2 if it's only supporting 16-bit instructions. Okay? All right, and then now we are coming back to the pseudo instructions, which we kind of like talked about. So pseudo instructions are instructions that that are not available so hardware does not understand pseudo instructions. But in order to make your life easier as a programmer, especially people who understand or learns other ISAs first and then moving to RISC-V, compiler in RISC-V supports this thing called pseudo instructions. Okay, for example, there is in this instruction called load immediate. Okay, which basically what it does is that stores the value of the immediate to the destination register. Okay, so let's say you want to initialize your register 10 with value 5. What you can write is li x10 5. Okay, so these are not. If I write this in, so hardware does not know that there exists li, but you can write it in the assembly language. the compiler will translate this into an existing instruction. For example, this one can be translated into add x10, x0, x5. Sorry, 5. Add I, x10, x0, 5. Right? These are equivalent. But this one is much nicer for a programmer to understand. It's li. That one is like weird add with x0. You might wonder, why are we adding x0 to 5? What is x0 and so on and so forth. So this is much easier for a programmer to follow. Okay? Same story with others. So people ask things like, why don't we have move? So we actually have move. Okay? So here's your move. So if you want to move one register to another register, write mv rd rs1. Basically what it does is writing rs1 to rd. Equivalent of this is adding x0 with that register and writing there. Someone asks, do we have negate? We also have negate if you want to. You basically subtract x0 from that register and you will have your negate. Someone asked about call. Call is basically a jump and link function with just the register RA is PC plus 4. Same story with return. And then all of these things that you ask, like branch less than, branch less than, branch greater than, and all of that. So essentially there is this list of pseudo instructions. This is not like our arbitrary instructions. This still needs to be supported by compiler, but this list is actually an official list of pseudo instructions for compilers in RISC-V. You can freely use these instructions as well. These are understandable from the compiler level. When it's translated into the machine code, these are translated in one of those instructions that I showed you. Okay? Just keep that in mind. I want to particularly talk about return and call because these are important instructions. So return and call is just jump, JAL, and JALR instructions. Okay, so ultimately they will translate it into JAL and JALR instructions. But the way that works is for return, we need to remember, like for example, we can have something like this. So essentially, when we're doing this, we are remembering that this is like current PC. My PC plus 4 is here. I'm basically saving this value into this x3, right? And then when I do this JAL, I basically jumped somewhere else in the program and I start running some instruction. At some point, I'm going to have ret, okay? So basically, how do I do ret? I write ret like this, JAL R, okay, x0, 0, x3. Okay, so what does this do? It basically says, remember the next address and save it to x0. Since I don't care about linking anymore, I put x0 there. I'm not linking anything. But what I'm doing now is I'm saying that go to the address x3, add it with the offset and jump to that address. And prior to that, long time ago, I saved PC plus 4 in my x3. This way I can actually return exactly to where I wanted to go. The important thing is that during this process here, I should not overwrite x3, okay? So I should be very careful not overwriting x3, because if I overwrite x3 there, then I'm cooked. So usually what I do is we use a specific register called return address register, which is one of the X's I'm going to show you later, that you don't touch it when you're calling a function. Okay? Yes. Multiple functions that you always link the last address to your return address, you go back, right? So yeah. You push, so if I want to change array again, first I push my array into a stack, I use the next array and pop it from the stack. No, x86 is also using register ultimately. So when you're writing in the assembly, you push and popping from stack, but that stack is actually like accessing the register. So it's the same thing. Same story with call, right? So for call, you need to jump to that particular address, and you need to remember where that address is. And again, these things will be taken care of by the compiler. You don't need to worry about where the address is and all that. All right, so here's another exercise for you. Let's say initially x10 is equal to 5 and x11 is equal to 3. After running this program, tell me what is the final value of x10 and x11. Let's say you start from here, right? So you start from here. Anyone wants to answer? All right, since I want to finish this, yeah. 10, 15, and x11, 0. Anyone else has find any other answer? Yeah. 20 and -1, okay. Probably, I think x11 would be 0. But yeah, 20 or 15. I think you're doing one more. You're doing an extra iteration in the loop. That's why you get different number than that. Right. 15, 0. How many of you get 15, 0? Few of you. Any like -1 and 20? 20 and 0? Okay. So just very quickly, so basically the way this works is that you start from here. As I told you, these are your labels, so these are not have any functionality. This is just for you to understand where you jump back when you want to jump back. So the first instruction that's going to be executed is this instruction here. This means that x20 will be equal to 0. So you're basically initializing x20 to 0. Then you're going to start executing this instruction. If you actually look into this instruction, it seems that x20 is some form of like a sum, right? So it's kind of a variable that kind of keep track of the sum. So what this does is that saying that x10 plus x20 and write the results to x20. So at this point, x20 is equal to 5. Then you are, this is your loop counter kind of thing. So you subtract this by 1. So here x11 becomes 2. Then you compare the two, the x11 with x0, and you jump back to this. Oops. You jump back to this if this value is not true. So this is branch greater than, means that if x11 is greater than 0, you jump back. At the moment it's 2, so you jump back. So you keep repeating this. This means that x20 becomes 10, x11 becomes 1, and then it's still, you jump back one more time. It becomes 15, it becomes 0. At this point, it's no longer greater than, right? So you take the branch, you no longer take the branch, so you continue forward, and then you move x20 to x10, so x10 at this point becomes 15, and then you return, right? So I think 15 and 0 is the correct answer. Make sense? What did I say about the return is basically this instruction, right? Jalor x0, some offset, which is usually 0, and whatever value that you use when we were jumping. When you're linking in your call, the register that you use for linking is the register that you're using for return. So the relationship between your call and return is that you use the same register for linking and jumping too. Yes, and you don't touch that register. Yeah, this is actually what we call a calling convention. So calling convention, you probably have seen it before. These are a set of rules that we follow. I'll answer that question. This is a set of rules that we follow when we want to guarantee correctness. For example, I told you, you don't touch the register that you use for linking. If you touch that, then you basically forget what the return address was and your program is broken. Okay? So there are three major rules. Usually there is a caller and callee, right? So the function that you start from and the function that you're executing. They usually agree on, okay, there's a set of things that you don't touch. So this is callee safe or caller safe. So either one of them don't touch the other ones. And then we also agree on some form of a stack, that if I manipulate the stack, I don't touch your stack, I move the frame pointer, I do things, and I go back and kind of basically clean up what I did so that when it returns back to the original function, nothing has been touched, okay? So these are the kind of rules that, if you want to call a function, this is the caller function, you put the variables that you want to pass on to that function into the stack. You invoke it by having a call function. In RISC-V, that would be a jalor instruction. Then callee, what they do is that it saves the registers of the caller. Okay, for example, the return address, it saves it into the stack so that even if accidentally it changed things, it can always pop it back. Okay, so it saves the old base pointer, it makes room for local variables, puts the return address into some register, restore the stack frame when it's done, and then finally it returns. This is the equivalent of the register file and registers that we use. So the left column is basically showing you the conventional registers that we have, x0 all the way to x31. We use this thing called symbolic names. Okay, this is the names that you can use when you're writing your assembly codes and compiler understands it. So basically, as you can see, x5 to x7 is temporary registers. x28 to x35 is also temporary registers. You can show them as T0, T1, T2, T3. These are registers that you can freely use to store, temporary variables and play with numbers and so on and so forth. The things that you don't want to touch is x1, x2, x3, and x4. These are pointers. x1 is the return address pointer. We can usually show it the RA, which stands for return address, or you can use x1, okay? So for example, I can write an instruction like this: add RA T0 T1. This compiler understands this. What this means is I go to this table and see RA is x1, T0 is x5, and T1 is x6. So these two instructions are equivalent to each other. Okay? Why do I want to use the symbolic names? Again, for convenience. That I don't want to remember, which register were I used for when I'm calling, you put RA. Which register do I use for manipulating the stack pointer, SP, and so on and so forth. Yeah. You always have a base pointer for your frame, right? So to use. Yeah. Good. So these are just conventions. Again, you don't need to remember or memorize any of these. You can always go back to this table. But what I'm going to say is that if you see an instruction like this, This is also perfectly fine instruction in RISC-V ISA convention, okay? This is just for making things easy for people to understand what's going on, okay? So these are, again, these are save register, means that don't touch these in your functions. A0 to A0, A1, and A2 to A7, these are function arguments. If you need function arguments, this is where you can find them, okay? And then x0, you can also show it as 0. Like literally the word 0, you can use it instead of x0. So that's also fine. So I can do something like add GP0, I don't know, add GP0 and 5. This means that its GP would be equal to 5. Okay? Which means that this is equal to add x3, x0, 5. Okay? Final things before I let you guys go. So this is kind of like the equivalent of the C types with the bytes that we use in RISC-V32. Character is 1 byte, short is 2 bytes, integer is 4 bytes, long is also 4 bytes, long is 8 bytes, and so on and so forth. So you can always refer to this, how this is equivalent in RISC-V. Okay? So this is the final set of instructions that you're going to see. This is actually the base instruction set that I said that we're going to focus in this class. So it's actually, I combine all of them, the JALs and JALRs. I think the one that I didn't cover is this load upper immediate. Basically what this does is whatever immediates that you provide is shifted to the left by 12-bit and save that number. So if you want to save the upper immediates, you can use this instruction. But this is the full set of instructions that you're going to see. And again, you can always refer to this table to memorize things. Okay? All right. So now that we understand this, the next question is, I have these instructions, but this is not what hardware understands. So the hardware does not understand BLT or BEQ. So what do I need to do is that I need to translate this in what we call a machine code, okay? So how does the machine code look like? The machine code looks something like this, that it's a 32-bit value. I divide it into different sections. For example, I will have an opcode, a destination register, source register 1, source register 2, immediates, and so on and so forth. Since different instructions use different things. So one instruction, for example, has RS1 and RS2. The other instruction has RS1 and immediate. The other instruction has, other things. So I basically divide this into groups. In RISC-V, we have 6 different groups: the R-type, I-type, S-type, B-type, U-type, and J-type. So next time I'm going to actually go over and kind of like show you how these instructions are becoming a sequence of zeros and ones in 32 bits that the hardware will understand it. Okay? Yeah, final question before I let you go. Yeah. What's that? This R. No, return is not an R-type instruction. What was the question again? It's a pseudo instruction, yeah. It becomes a JALR. Yeah.